Welcome everyone. I'm Ollie, and this is what I got up to in my placement year here at KISS. So I'm going to start off with a section just about me and how I got here, and then I'm going to look at some of my projects, and then I've got an other stuff section. I didn't really think I'd have time to go through everything that I've done in my year, and so I've kind of crammed everything else into an other section at the end. So first, just a little bit about me. So my name's Ollie. I'm studying aerospace engineering at the University of Bristol. So I was looking for placements kind of everywhere. I knew that I wanted to work in the space industry because, well, I've always been into space, kind of all aspects of space, and that's why I started an aerospace engineering course. Yeah, so I was applying to loads of places, and I eventually saw an advert for KISP, and I'd heard of KISP through their involvement with the spaceport Cornwall, and so I was like, oh, that sounds like a really good opportunity. Let's apply there. So I sent in my CV and covering letter, and then had a couple of interviews, and then amazingly on my birthday, I got offered the job, which was quite cool. And yeah, here I am. So once I'm finished here, I've got 2 more years left of my degree. And then we'll see what happens next. So now we're going to look at some of the work that I've been doing while I've been here at KISP. So as I'm sure some people are aware, a lot of what I've been doing since Christmas has been on SAT-LL, a training satellite that we're developing. So the idea is that it's a functionally representative model of a satellite. It will do everything a satellite should, but the ways in which it does it are it's not always flight representative. It's maybe in a kind of cheaper, easier, more user-friendly way. And obviously one of the key areas in which it deviates from flight standards is in the structural design, which is where I've done most of my work. So obviously a CubeSat would usually have an aluminium alloy kind of structure, but we couldn't really give SAT-LL that because then it would cost thousands of pounds just for the structure alone, and no one would buy it. So we knew that we had to have a 3D printed structure so that we could make it quickly and easily in-house using our 3D printers and laser cutters. The design went through a lot of iterations. These might all look quite similar, but each change you have to make kind of 50 other changes. So like you move one thing up and then you have to move everything else down a bit. And then it's a lot of kind of balancing different things. The general principle of having subsystem boards which slot into a backplane kind of remain the same. So you do have these kind of shelves in the structure, but all the stuff around that has kind of changed and been tweaked. As you can see, the height changed quite a bit throughout the process. But eventually we got to this design, which is the current kind of final version. I say final, it probably will change more as we develop other things. But this is where we are at the moment. I've labeled some of the kind of key features on there. I won't go through all of them now, but there's a lot of things here that allow us to demonstrate actual flight functions. We've got like a deployer so that we can demonstrate separation switch functionality. We've got a deployable magnetometer so that we can show a deployable mechanism on a spacecraft. And then we've also got other things which aren't as flight representative, so things like having removable front covers, which are transparent. That's obviously more for the teaching purposes, so that you can take the front covers off, remove boards, test on them individually. And so that's where it kind of deviates from actual satellite. And once we'd come up with the design, we started making it. And it was kind of an iterative process. You'd kind of make things and then think, oh, I've got to tweak that. And so you kind of go back and forth between designing and making. But eventually we got to this final structure, which I actually have here with me now. And it was really good to kind of get a proof of concept of what we'd designed. We've got some of the kind of mechanisms here showing them working. Got our nice deployable antennas which pop out the sides. Yeah, it's really been quite cool to see it all come together and be involved right from the start through to having an actual thing in front of you that you can hold, and will hopefully be used kind of in the future SAT-LL development. a lot of things, especially when you're manufacturing, there are a lot of things that you maybe don't consider when you're designing. So things like tolerances and stuff. And yeah, ensuring you've left enough, like a big enough hole size to include heat set inserts, and a lot of things that you don't really consider when you're designing, but you have to consider once you actually start manufacturing them. So that's been quite good experience to get. And then I've not just done not just been involved in the mechanical design. I've also had some involvement in the electronic side of things. I don't really have much electronics background, but I've had the opportunity to kind of work on some electronics. So this is the back plane here, which is effectively carrying all the power and signals between each of the subsystem boards. So I've been working on this. I did have some help from Free here at the start, but it's kind of I've taken it over since she's left. And as well as that, I've also done some work on developing an imaging payload, which I unfortunately wasn't able to finish, but it's in a quite a good place for Adam to pick up, and he has already started picking up on it. So that's quite good because he can kind of ask me for help or figure out what I've been doing. Yeah, and then as well as that, I've also been helping to assemble some of the boards, so things like debug board, sun sensor board, and maze motor board. I assembled those using the pick and place machine and reflow oven, and then also did a little bit of testing on sun sensor boards, just to kind of get a proof of whether the boards actually work, which they don't always. So now for something completely different. So Kismet is our system modeling tool. It's an Excel-based tool that we have here at KISP. I'm sure some of you will have heard about it, and maybe not really seen anything of it. It effectively allows a range of mission parameters, and then performs a mission analysis based on those parameters, things like power budgets, and delta V budgets, things like that. And so one of the first things I was asked to contribute to the system model was a data budget. So initially, I designed a static data budget, which effectively models flows of data. So it measures kind of the volumes of data that you can get down per day or per link session, and it takes data from the ground station access data tool that I also created, to give kind of average pass times and things like that. So you can input SDK data into the ground station access data sheet, and it will tell you kind of some useful outputs from that data. And then once I'd done that, I moved on to developing a dynamic data budget, which is more about the flows of data. So it kind of takes each time step and measures the flow, the amount of data within each store over time. So you can plot kind of a nice network of data stores and nodes and things, and see how the flows of data between each of them kind of fills up the stores, and it allows you to kind of helps you to size your data stores at each point. And then finally, on the system model, I moved on to making a solar panel visualizer tool, and this is the coolest tool, so I'm going to go into it in a bit more detail. So in previous versions of the system model, you had to define your solar panels by defining the normal vectors to each panel. And while that's easy for kind of body-mounted solar panels where you've just got kind of +1, -1, +1, -1, in this it becomes a lot more difficult when you've got deployed panels at kind of weird angles. So we wanted a tool that allows you to easily define your solar panels, and also create some kind of image of them so you can see that you're modeling the right thing, and then also outputs some normal vectors so they can be used for subsequent power generation modeling. And so this is the tool that I created. So you simply define your satellite dimensions. You create a kind of rough box size shape, and then you can add up to 10 panels to that. You can define whether they're body mounted panels or deployable panels. You define the face that they're mounted to, and then for deployable panel, the angle and the axis about which it's pivoted. And then you can generate a cool diagram and spin it around, and it will output the normal vectors in the table on the right hand side. So this is it doing a spinny thing, which is quite cool. I didn't realize Excel could do this, which is yeah, it's been quite a learning experience. Getting to do some kind of VBA coding and things like that to get it to do interesting stuff. So now a little bit on Comet Interceptor. So it's an upcoming ESA mission, which I've had some minor involvement with. So Comet Interceptor, just for those who don't know, is, as the name suggests, it's going to be tracking and analyzing a dynamically new comet, which is basically a comet which hasn't been in our solar system or hasn't been in our solar system for a very long time. And so hopefully it will give us a kind of better understanding of the formation of our solar system. And so the work KISP has been doing has been developing some of the software for one of the instruments, the MERMIS instrument, which is the Modular Infrared Molecules and ISIS sensor. And no, I didn't remember that. I have got a note here to say that. Yeah, so my task specifically has been to define a telemetry and telecommand database. So that's basically creating a database of all the telemetry and telecommands that could be sent to or from the instrument, and then they can be used for kind of simulating the signals to or from that instrument. And so this has been like a really good project because it's kind of given me exposure to kind of communication standards like CCSDS, things like that. And it's also given me experience of working on an external project. So I've had to kind of collab external people, and it's been quite a cool experience really to get experience of that while I'm still at uni. And now on to KernOSAT. So I've done quite a range of things on KernOSAT. So quite early on in my placement, I was involved quite a bit with kind of AIT support. So we had quite a kind of intense phase of testing quite near to when I started. So I was doing kind of writing mechanical inspection procedures, helping to carry out those procedures in on the flight equipment. I was helping to do continuity and isolation plans on test harnessing that we'd made. Also creating kind of handling documents to help kind of easily show how you should be using the items. And then on the other side of that, I've also been working on quite a bit of mechanical ground support equipment for KernOSAT. So we've got the harnessing jig, which there's a picture later, and also some protective solar panel covers, and also a solar panel deployment test jig. So they're all kind of things that we can make quickly and easily in-house. And so it's just about that it's designed in a way that isn't going to damage anything that costs a lot of money, basically. And then on top of that, I've also made a nice simplified CAD model of KernOSAT, which is actually the one you can see on the screen now. So it's kind of so that we don't get in NDA trouble when we release things. So here are some of the MEGSI that I've been creating. So the harnessing jig on the left is effectively for kind of simulating the satellite so that you can manufacture the harnessing and like test runs between different parts of the satellite. And it's also meant to give a kind of structural representation so that we can kind of simulate the building of the satellite. And then we've also got things like the solar panel deployment test jig just at the side or in the middle there, and our protective solar panel covers, which are they've all been made. So that's pretty cool. So now on to some kind of other stuff that I've been up to during my placement. So we've got, I think one of the first things I got asked to do while I was here was design a rotary air bearing table, which seems to be quite a bit more difficult than I hoped. And I did make a design for it, and it's never actually went anywhere, which is a bit of a shame. But that's just how things are. And then we've got things like I did a lot of research for NGMP, so looking into competitor platforms, payloads. I've created a nice big kind of database of each of them, which hopefully has helped with some of the NGMP developments that have been made. As well as that, I did a bit of work with Freeha, where we were looking at kind of configurations of NGMP and what kind of options we might give NGMP. And on top of that, I've also done a lot of CAD to do with NGMP. So for one of the proposals we did, I think late last year, I made some concept CAD for one of our proposals. And I've done a few other kind of concept CADs for NGMP throughout my placement. As well as that, I've done a range of kind of Excel data analysis. So we had one project that involved quite a bit of STK data, and I was kind of helped out writing some code to help us analyze that in Excel. And yes, that was quite cool. We've also had things like the mission design exercise that I've been engaging with. So each of the graduates and myself got given a fictional kind of customer, and we had to develop a mission concept for them and kind of present that to Vicky, Ange, and Catherine, and get kind of a lot of useful feedback from that. And that's been quite cool because it gives you very much like a clean slate. You've got to come up with everything yourself. And then on top of that, I've also been to quite a few industry events. So here we've got a few me kind of at places. So we had Spacecom Expo in March, which was probably the main event that I've been to. And at that, we kind of speaking to loads of kind of industry professionals, getting people excited about what we're doing with SAT-LL and Essential Sat, helping out with demonstrations and things. And then we also had one of my first kind of event experiences was at VentureFest in November. Again, kind of speaking to other innovators about what KISP does. It's just a good opportunity to get a chance to kind of speak to people and get out there. And then I went to a careers event in April at Alton College, where we basically tried to get people excited about careers in space. And so we were demonstrating Essential Sat and showing that these things can do cool things, and that they're a lot more sophisticated than perhaps we might expect.
On a serious note, I guess what's the one thing that you've learned over your year that you're going to take away? Have you got like the thing that you go, if ever I forget everything, this is the one thing that I've really learned and is useful?
I'd say probably the biggest thing I've learned is just to ask questions. Just don't be afraid to kind of ask silly questions, because that's when you learn the most. It's better to kind of say something rather than just sit there and kind of be confused. Yeah, I'd say that's probably the main thing I've learned. It's just to make sure you keep a dialogue with people.
If you don't know the answer to a question, there are probably other people sitting in the room that also don't know the answer and are too scared to actually ask.
Yeah. Cool.
Super. And you've obviously done a lot of different things. So
yeah, there's been a real variety of stuff that I've got involved with.
That's helped you, really and
yeah, a lot of different experiences, which has been really cool.
I was just going to ask, if you're going to do the year again, would you do anything differently?
I think at the start I maybe wasn't getting as stuck in as maybe I should have. Kind of a lot of my projects involved making things, and I think I often hesitated in the kind of design phase and then didn't get around to actually making the stuff. So I think I would have kind of knuckled down a lot sooner and started kind of producing things earlier and testing things out, because that's kind of how that kind of helps your designs as you're making them. So yeah, really just hitting the ground running more, I think, would be my answer.
But I think it's fair to say that I don't think any of us ever at any point, and Catherine and Ange, feel free to contradict me, but ever thought that you weren't getting stuck in or weren't like getting on. So I think that's it's good that you've like learned that, but I think the
Mm.
perception has always been that you have got stuck in and you've given everything a good go and so on and so forth. So
Thank
just
you.
so you
That's
don't
very
feel
kind.
like we were at the beginning going, oh
Mm.
golly, you know.
Yeah.
Sorry, Angie.
Sitting around doing nothing, wasn't it?
I know, shocking.
I think the other thing that I actually liked when you did your presentation just now
Mm.
is that you have realised that you have to try things out, and
Mhm.
designing for manufacture is quite key,
Yeah, it's a
because
skill in
you
itself.
mentioned that you design stuff, but then when you put it together or do it, it doesn't work,
Mm.
and that is a skill in itself, and that's a
Mhm.
good thing to take forward, is that design for manufacture. Think about how you're going to make things when you're designing it, because
Mm.
and it's the same with spacecraft. Think about how you're going to operate it when
Mm.
you're designing it. So that's a very important skill as well. I'm pleased to see that you've realised that that's something you have to do. So.
Yeah, I think that's definitely been something I've learned a lot, is actually turning designs into actual physical things has been a kind of real kind of learning point. But yeah, it's a good point. Yeah.
So,
Yeah, and I'd like to say thank you to everyone, actually. You've all been like really patient with me and helped me a lot in kind of developing. So yeah, thank you to everyone. It's been a really fun year, and I've learned a lot. So thank you.
You've seen how appreciated you are within the company, and I echo everybody's thoughts that you've been an excellent person to work with and great fun and fitted in really well, and you've produced some excellent work. So thank you very much. And we, on behalf of the company, we wish you well moving forwards, and yeah, keep in touch.